Friday of last week, I said that what we would do next is the kind of substitution that lets you take either a sum or a difference of squares, and by making a trigonometric substitution, convert to a single term, which is a perfect square, so that if you have a problem that has all that under a square root sign, then you're doing the square root of a square, and then that's the absolute value of your trig function. And you think of it that you're working in the first quadrant where the trig functions are all positive, so then the absolute value issue goes away, because the absolute value of something that's positive is just whatever it is. So what you scheme out of is working with a sum or difference of squares, but the price you pay is now you have to work with trig functions. Then you do your antiderivative, and then you have to go back. You have to substitute back. So that's what I'm saying there, essentially. So the three forms, then, with which we will work, which are the three that I put on the board at the very end of class last Friday, are a square plus u square. So then use u equals a tangent x. The a is a constant. And then use then you get a square plus a square x square. Then you factor the a square, and then you use 1 plus tangent square equals secant square as your trig identity. So you've converted from two terms to one, and that's the gain, but now you're working with secants. Nevertheless, as you'll see in the homework examples, it pays to do this. If you have the difference of squares where there are two possibilities, you can either have the difference of squares where it's variable minus constant, or you can have the difference of squares where it's constant minus variable. So the two possibilities with the difference, there's only the one possibility with the sum, because u squared plus a squared is the same thing as a squared plus u squared. So there are three situations and not four that we work with. So if it's variable minus constant, the replacement is secant. U would be a secant, then this becomes a square secant square minus a square, so you factor, and then secant square minus 1 is tangent square. So now, once again, you have one term, which is the gain, and it involves trig function, which is the price you pay. And if it's the other way around with your difference of squares, a square minus u square, then you could use either sine or cosine, but typically use sine. That's what your book's doing. There's no reason not to. Then you'll have, as you see, a square minus a square sine square, factor the a square, and then 1 minus sine square is cosine square. If you had done it the other way around, if you'd used a cosine, then you'd have ended up with a square minus a square cosine square, and 1 minus cosine square, and then you'd have ended up here with a square sine square. So you could do it either way. So if you think of your x as a first quadrant angle, so the trig functions are all positive, then you don't have to worry over absolute value signs. so we do that. And in working to get from x, as I've used it here in my substitutions, back to the original, you notice that we always draw right triangles in the first quadrant set. So look at problem 1 of the 8.3 homework. So we have the integral dx over square root 9 plus x squared. And you see that's this form, the sum of squares. So the a is 3 then. So x is 3 tangent. Since the variable here is x, you need to use some other letter for your angle. So I use t. Use anything you want. X is 3 tangent t then. As I said back here, you're going to have, when you make your replacement for your sum of squares, 1 plus tangent square with the 9 factored out. You see here, your 3 tangent square become 3 tangent rather becomes 9 tangent square. You factor the 9. So then you have square root of 9 secant square. And on top, you have to replace the dx by what it is for the appropriate trig function. Derivative of the tangent is the secant square. And then your differential changes from dx to this derivative times the differential in the new variable, dt. And so you have the 3 secant square dt on top and square root of 9 secant square, which is 3 secant on the bottom. So you have the integral of secant. And if you were here last week, a week ago on the Thursday, you remember that what we worked with was the integrals of trig functions. And we had some that were sine and cosine, and then we had some secant and tangent ones. And we did secant cubed, integrating by parts, if you remember. And we did the secant with the trickery that you take secant and you multiply and divide by secant plus tangent, and write them one way on top, say secant plus tangent, and then opposite tangent plus secant, say on the bottom. And then turns out that what's on top, when you multiply by the original secant, is exactly the derivative of what's on the bottom. So if what's on the bottom is secant plus tangent, and you have the derivative of that on top, then your integral is going to be log. And so let me get a pen and fix my plus sign. So anyway, one reason that we did the integral of the secant last week was that we'll be led to that particular integral in problems of this type when you have made the substitution to replace the original sum of squares. And now, this is not yet the answer, because this is the answer in terms of the new variable t, and if it's an indefinite integral, you have to get back to the original variable. If it were a definite integral, then you could change your limits on x to new limits on t, and then you could work from here with the new limits. But as it is, what you do is you draw a right triangle in the first quadrant. And your relationship here, if you solve for tangent, is it equals x over 3. Well, in your right triangle, if you put your angle down here in the corner, your tangent is side opposite over side adjacent, right? Right triangle trig. So then that means if x is here and 3 is here, your tangent of t is x over 3. Then you use the law of Pythagoras to get the third side, and you notice that the third side of your triangle is exactly the two-term expression that you did all this trickery to deal with. That's always the case in these problems. When you're going back to the original variable, you use a right triangle drawing, and what comes from your substitution is a trig function equal a quotient, because they are ratios of two sides of a right triangle. And so you identify your two sides from the numerator and denominator in the quotient that you're defining with your trig function, opposite over adjacent or opposite over hypotenuse if it's a sine, and so on. Law of Pythagoras gets the third side, which will be, or which will involve anyway, exactly the sum or difference of squares that you started with. So that's kind of a check. So then from here, you can say cosine is the 3 over the square root, and then secant is 1 over the cosine, so turn the cosine upside down. That's how I do it. I can remember the ratios for sine and cosine and tangent, and then I turn them upside down if I have a cotangent or a secant or a cosecant. Okay. So then your answer for problem 1, you see, what you have now is you have secant in terms of the original variables, and you have tangent back here. So your answer, which is log secant plus tangent, is log secant, which is your square root over 3, plus tangent. And when you do the integration for secant, you always put absolute value here, log of absolute value, because log is not defined unless what you're taking the log of is positive. But when you look at what you have here, you have a square root of the sum of squares. There's no way that's going to be negative, and your x is not negative because you're assuming that you're working in the first quadrant to begin with. So you really don't need the absolute value there. It doesn't hurt if you want to write it, but you don't need it. Notice there's a little more trickery here yet. I wrote this plus a constant with a subscript, C1. Now, you notice you have a common denominator on these fractions. And so you could have written this square root 9 plus x squared plus x, all divided by 3, just as well. Okay, the log of a quotient is the difference of the logs. So you could have rewritten this as log of the sum of the two numerator terms minus log 3 plus constant C1, and then constant C1 minus log 3 is just another constant you could call C2. And So you could write your answer log of the square root plus the x plus some constant. And that's what you find in the back of the book. So you can play tricky games with constants on these indefinite integrals. A question here on problem 1. There's trickery here certainly, but you notice that with tricks of this sort you can do the kind of looking integrals that we have in this section that involve sums or differences of squares. And often that sum or difference is under a square root or something like that. Here's a definite integral, and you notice you have a difference of squares, the constant minus the variable type. And so that's your sine cosine type substitution. So based on what I said back, I would take x as 3 sine, then your dx is going to be 3 cosine, and then your 9 minus 9 sine square is going to be in here as a 9 cosine square, and then when you square root 9 cosine square, you're going to get 3 cosine. So this is going to become 3 cosine without the square root, and you're going to have 3 cosine up here from the dx. So the integral then is going to be 3 cosine t to the dx, square root of 9 cosine square, which is 3 cosine t in the bottom, dt, and since it's a definite integral, the thing to do is get the appropriate new limits. So we have x equals 0, and we have x over 3 equals sine t, so sine t is going to be the 0 over 3, so sine then is 0, so the t is 0. So the new bottom limit on t is also 0. But for your top limit, your x is 3 halves, and your sine t is x over 3, so it's 3 halves over 3, so sine t is a half. Okay, so if sine t is a half, t is arc sine, 1/2, which is your 30 degrees. But you don't say degrees. In calculus, it's always radians. Why is it always radians in calculus? Answer: because the derivative of the sine is not the cosine unless you're in radians. If you're in degrees, the derivative is pi over 180 times the cosine. And so radians were cooked up so we don't have to say pi over 180 every time we open our mouths with the calculus one. So it's always radians. And so it has to be pi over 6. And as we've already said, these are identical. So you have the integral 0 to pi over 6 dt, which is t, 0 to pi over 6. So your answer is pi over 6. And you see the degrees or radians issue is important because the answer is pi over 6. The answer is not 30 degrees. Again, if you look at the sides of the right triangle, where sine t is x over 3, Here's your x, your hypotenuse. Law of Pythagoras gets you the third side, and that's exactly what you were playing all of this game to avoid, is dealing with this square root of the difference, 9 minus x squared. That's always going to be true with these substitutions and using the right triangle to get from one variable to the other. The third side of your right triangle will involve anyway the sum or difference of squares that forced you into all this. Now take a look at 7. You have the square root of 25 minus t squared. Now, if you think back a couple of weeks, you should recognize that we have this integral. So what I have here is a review for a minute. When we were in 6.5, that was the kind of thing where we, if you remember the 6.5 problems, a lot of them were work done by variable force like Hooke's law and whatnot, or lifting the bucket where the water was leaking out in the sand or whatever. And then we had in that same section, we were pumping water, somewhat like the problem on the test, where we were pumping the liquid chocolate. And then we had the ones where we had force due to the weight of the water, or could have been any other fluid, on one side of the wall of the container. And problem 36 was one of these, where the water is 6 feet deep, and you have this half circle window, if you want to think of it as if it's a big tank and people are looking at the sharks or whatever is in there. And so the top here was a foot down. This had a radius of 5 feet, and so the high point here is a foot down from the free surface. And we were calculating this force. So we had a strip across here where the window part is. If you take your origin here so that y is the height to this representative slice, then it's 6 feet up from the origin to the free surface of the water, and 6 minus y then is the depth. You remember that your Pascal law is that the pressure is the depth times the density of whatever the stuff is, the water, say. And then your force is, well, first of all, it's pressure is force per unit area, so force is pressure times area. So it's density times depth times area of the representative slice. So this strip has a length of 2x if your y-axis is here and it's x each way, right or left. And we have the formula for the circle when the origin is here, which would be the sum of the squares equal the squared radius. So then your x, if you solve this for x, is square root 25 minus y squared. That's there to there, and it's the same going to the left. So your length of your slice is 2 square root, and that times dy is the area, and then density times depth times that area is your force against this. So we had this a couple weeks ago when we were doing that problem. Well, if you remember back when we were doing that, our force would be the integral here, and you see there are two integrals, because there's the density times the 6 times the 2 times the square root, and there's the density times the minus y times the 2 times the square root. So that gives you these two integrals to do. And this one we could do, this was a u substitution. If u is 25 minus y squared, the du is the minus 2y dy. And if you can remember back, we had this one, and I said at the time, this is something that we don't know how to do. And I referred you to the formula in the back of the book, number 45, in the appendix. And we did this one in class by referring to that formula and substituting into the formula. Okay, so this is basically that same integral, see? Whether it's 25 minus t squared dt or 25 minus y squared dy, it's the same issue. So now we will see how you do it. In other words, how they got the formula that's in the back of the book. If you can remember the formula in the back of the book, it involves an arc sine. So with this morning, so far, that ought to make a connection. We do these trig substitutions. We do, if it's a square minus u square, substitute in a sign, and so that's where that arc sine might be coming from. Okay, so back to here then. We let t be 5 sine x, square root of 25. dt is 5 cosine x dx. So then this will become 25 times 1 minus sine square. And of course, that's 25 cosine square under the square root. And of course, that's your 5 cosine. Then you also have dt is 5 cosine x dx. So your square root here is 5 cosine x. Your dt is 5 cosine x dx. So altogether, you have 25 cosine square dx to do. So then what you want to do is think about your recipe from the trig class. So we go over here to the recipe box where 2 cosine square is 1 plus cosine 2x, and 2 sine square, for good measure, is 1 minus cosine 2x. You use those so much in doing integrals by hand that it's worth trying either to learn them or to learn where to find them, let's say. And so using that, you see, I'm replacing my cosine square by the 1 plus cosine 2x. See, it would be over 2, and then the 2 I put out in front. So there's the 2 that would be this 2. And so when I integrate the 1, I get x, and that's where that arc sine is going to come from. And then when I integrate cosine, I have sine, and if it's cosine of a times x, it's sine of a times x over a. So now we make the same substitution triangle that we've done in the others. So our substitution was sine x was t over 5. So there's t, and there's 5, and there's x. And this over that is sine. And then your third side, sure enough, that's the square root that you're dealing all this trickery to try and get away from. And so your cosine is the square root over 5. So the reason that I need cosine as well as sine here is that I have sine 2x. So I have to use a trig identity that sine 2x is 2 sine x cosine x. You had problems of this sort in either Math 144 or Math 147 where they give you the triangle and then they want you to tell them what side of 2x is the. So what you have to do is take the triangle and get sine x and cosine x as you read it from the triangle, and then use the trig identity for sine 2x, that it's 2 sine cosine. I'm sure you remember suffering with a lot of those things like that. So then the sine 2x over 2, which is 2 sine cosine, notice those 2's cancel, and then you have sine x, which is t over 5, and cosine x, which is the square root over 5. And then from this first part, where you have the integral of dx giving you x, the x is your arc sine of t over 5. And so that's going from the x that's here, when you do this integration, to arc sine t over 5. That's why there's the arc sine in that formula in the back of the book, number 45. So then finally, you could go on from there. This was an indefinite integral, so you would just be leaving it with the arc sine and like this in terms of the original variable. In the formula 45, instead of 25 minus the squared variable, it's a square minus the squared variable. So then what you would have, if you actually look at the formula in table T2, instead of this you have a square over 2 and arc sine of, I think the variable actually is x over a, and then you notice this times this is the a square, and so then for this part you have your variable over the 2 and then the square root. So the formula is equivalent to this, although it's written just a little differently. So that's where it comes from anyway. It's this section of the book. Meanwhile, take a look at number 10. So this is variable square minus constant square. See, so this is a different case from the others. And the reason that it says x is greater than 3/5 is so that you're not trying to take the square root of a negative, and by greater, then this is in fact positive here, so you're not dividing by 0. See, if x were equal to 3/5, your denominator would be 0, and you're not allowed to divide by 0. And if x were less than 3/5, you'd have a square root of a negative, and you can't do that. So that's why that's in there. So let x be whatever would be your square root of this number over that one, which in this case is 3/5 secant. And then your dx is 3/5 secant tangent. And then you see, if you have done that, Your 25x minus 9 is 25. The x is the 3/5 secant, so the x square is 9/25 secant square minus 9. You notice the 25's cancel, the 9 factors, and your secant square minus 1 then will be your tangent square. So your square root becomes this square root, which becomes this one, which becomes 3 tangent. And we're thinking of this in the first quadrant. So the original problem then, I factored the 5 out, and my dx was 3/5 secant tangent and dt, and then my denominator was 3 tangent. And so the tangents cancel and the 3's cancel, and this 5 cancels that one, so I end up just integral of secant. And we talked about how you do the integral of secant, log secant plus tangent here. And so what you have to do now is replace secant and tangent to get back to the x. Well, if x is 3/5 secant, then your secant is 5x over 3. Okay, and then your cosine is 1 over secant, it's 3 over 5x. So I go back to sine or cosine to draw my picture, because that's the limit of my mental capacity. So I'm honest. And so if I'm back to cosine, I know, oh, that's side adjacent over hypotenuse. So I make my numerator the side adjacent, and my denominator is the hypotenuse. And then I do the law of Pythagoras for the third side, and sure enough, that third side is this same square root that we were working, that we were doing all of this substitution game to try and get away from. It always comes back to you as the third side of this substitution triangle. And so there it is. Okay, so then when you want to form secant and tangent, this third side will appear somewhere. Okay, so your cosine is 3 over 5x, so your secant, which you're replacing here, is the 5x over 3. And then your tangent is opposite over adjacent, and so this appears as the numerator in your opposite over adjacent quotient. So finally, you could write this. Now you can play the same game again with logs. So you have a common denominator. So you have log 5x plus the square root minus log 3, and then a new constant is the original one minus log 3. So you could say it like that. In the book, they wouldn't bother with the subscript, so the book will just have log of 5x plus the square root plus constant. And one thing it will have is its log of the 5x plus the square root is the argument of the log, so I think that.
Another bracket.
I had one there, but it wasn't very clearly printed, I think. I think you can see now that the 5x plus the square root is the argument of the log. That's what I'm trying to say, anyway. Okay, any question on this?
Fifth from, could you remind me how you got the secant?
Well, what we're doing, you see, if you have a difference of squares and it's variable minus constant. That was what we were talking about here first. I used u here instead of x. If you let the u be the square root of the constant times secant, then when you have major replacement, you'll have your square, secant square minus your square here. You factor that, and then you say secant square minus 1 is tangent square.
Okay, thank you.
So it comes from the trick you use if you have this situation where it's variable square minus constant square. Yeah, you have your bag of tricks. You have your three basic forms back here, and you have to know or figure out which trick is appropriate to which form.
Okay.
So much of this type of mathematics is a bag of tricks. You'll find that's true in the differential equations class. If you take that, there's a it's much of this same kind of calculus, actually. That's why the Math 175 is a prerequisite to the 333 class. What you do in third semester is not near so much of this sort of trickery and doesn't relate so much to the differential equations. Anyway, look at this one where you have the sum of squares. And the reason that I wanted to talk about it, we've talked about sum of squares tricks and some of these others, but what's interesting here, this is not a proper fraction. A proper fraction, when you're talking algebra, the degree of your denominator polynomial is greater than the degree of your numerator. But you see, as polynomials, these are the same degree. So if you have an improper fraction, the first thing you do is long division. You divide it down. And so that's up here. So this is Math 25. And so we set up our division problem, and whatever is here is exactly what it needs to be. So if you take this times that, it will be identical to what's above it in the dividend. And so this is a 1 because 1x squared gives you this x squared, which is just like that. So when you subtract, the first column disappears. That's your gain, isn't it? And whatever else might have been here will be in another column. For your answer up here, for your quotient, you'll take it times every term you have in your divisor. And so the 4 will go over here. So you have to think of it that there would be a 0 here for this to go underneath. You can just as well as not say you're dividing into x squared plus all the zeros you might want to write. And so finally, when you subtract, your remainder will be the minus 4. So that means that your original fraction becomes your quotient, the 1 dx, and then the minus, and then the 4 dx over this. So then the integral that is to be done that's of the type that goes with this section is the integral 4 dx over x squared plus 4. And you can factor out the 4. So you're just looking at this. Now, this is a form that you actually learned in Math 170. If you look at the table that they give you at the start of Chapter 8, which is kind of a summary of the Math 170 recipes, you'd find that the du over a squared plus u squared is 1 over a arctangent. So if you've wanted to just say, well, I've learned that, and go to the answer, I wouldn't argue with you. Otherwise, you can do the substitution. So, doing the substitution, which proves the recipe, you have your sum of squares type situation, so the x will be the square root of the constant times tangent, and then the dx is the derivative of the tangent, which is the secant square, and then 4 plus 2 tangent quantity square gives you 4 times 1 plus tangent square, which is 4 secant square. Which reminds me, I better do this. And so, also, if you're letting your x be 2 tangents, your dx is 2 secant square. And so, what this will become then is your dx, which is your 2 secant square dt, your x squared plus 4, which is the 4 secant square. And you notice the secant squares cancel, and the 4's cancel, so you have 2 dt, which is 2t, and then where tangent t is x over 2, t is going to be the arctangent. So you're going to end up with your 1/2 arctangent x over 2. The 2 into the 4 goes 2. So then let's look at 17. We have, again, the sum of squares. So if x is 2 tangent t, you'll have 4 tangent square plus 4. Your dx will be 2, derivative of tangent is secant square. Your x squared plus 4 would be 4 tangent square plus 1, which is 4 secant square. So your square root will become 2 secant. So your denominator here will go to 2 secant, and if your x is 2 tangent, you're cubing that, so you'd have 8 tangent cubed, and then your dx would be 2 secant square. So this in blue is this one. So then what you have, you notice, is the 2 would cancel, the secant would cancel, so you have the 8 that I factored out, the secant, and the tangent cubed. And so I've come down here with it, and to do the secant tangent cubed, what I do is I factor the tangent cubed into tangent, square, and tangent. And then I replace the tangent square with secant square minus 1. So I have this 8 is here. My tangent square is secant square minus 1. My secant is here, and I put it with the tangent because if u is secant, so this is u square minus 1, secant tangent dt is du. So finally, my integral here is 8 u square minus 1, all this is du, which I wrote up here. And so the u was secant then, as I did it, and my du, secant tangent dt, was this part. So then I integrate u squared to get u cubed over 3, and this to get u, and then I substitute back to write the answer in terms of secant. But I still have to get back to x. So you see there's a double substitution here. There was a u substitution to do the integral that was tangent cubed times secant, where I split it up first like this and then let the tangent square become secant square minus 1, and then called the u the secant, and so on. And I had got into secant and tangent by making that substitution that x was 2 tangent to get from here because of the square root sign. So I still have to get back to x, where I had let tangent t equal x over 2. So here's my triangle. Here's my x, my 2. My third side, sure enough, is the square root part that we got into all this trying to avoid. And then I can look at this and I can see how to write cosine, and therefore how to write secant. So I can replace I can factor my 8/3 and write my secant cubed as secant square and secant. So here's my secant. And then I can write my secant over here. And so I now have the square root as a common factor. And the 8 here is canceled. And so then I have x squared plus 4 over 3. And I take this 2 into the 8, so I have 4. And then I can get this over common denominator. And so this is what the book has. So there's quite a bit of algebra here and quite a bit of trickery, but I can actually get to what they have. Okay, then just a minute, I want to get my sign-up sheets. We have the sum of squares, so again it's going to be a tangent, and the x squared plus 1 then is 1 plus tangent square is secant square. So we have square root of secant square, and then our x squared here will be tangent square, and the derivative of tangent is secant square. So we have secant square, tangent square, and then the square root here of secant square. And so this secant would cancel one of those and leave you a secant on top, and your tangent square is there. So I think the best thing to do with this one, and this is why I thought I'd end up with doing it, is to go back to sine and cosine. Sometimes the dealing with the other trig functions becomes more trouble than it's worth. You can, sometimes you can be too clever by half and outsmart yourself, I think. I think this is one where it's really safer to just convert everything back to sine and cosine. When I took trigonometry in high school, which of course is a long, long time ago, I can remember my high school trig teacher saying that if you're working with identities that are these other functions and you don't see what to do, change everything back to sine and cosine. I think this is pretty good advice here. So secant is 1 over cosine and tangent is sine over cosine. So then you can invert and multiply, and you see what you're going to have is you're going to have 1 over cosine times cosine square over sine square. So this cosine will cancel one of these. So you'll have cosine over sine square. So then if you let the u be sine, the du is cosine t dt. So this becomes du if this is u squared. Okay, and then you can rewrite that with the negative exponent, and then just add 1 and divide by your new exponent. Now you still have to get back to your x finally. So you have minus 1 over u, so minus 1 over what you call u, which is sine. And now to connect to x, remember that you said that tangent t was x over 1. So here's t, and tangent is opposite over adjacent. Here's your third side, which of course is always the radical that was in the original problem. And then if you are looking at this, sine is x over the square root. So 1 over the sine then, which of course you could say is cosecant, you can just flop this over and you have your minus. So finally, in terms of x, you get an answer like that. So this is a problem that's not really that hard, except that you have to figure out how you're going to do your integral of secant over tangent square. And I think really that this is the simplest way to do it. Well, what we will talk about tomorrow is what we call partial fractions. If you have an integral to do and you have a denominator which is a product of two factors, let's say you have dx over x plus 1 times x plus 2, just to say something that's simple. The way that you do that type of thing, as you'll see tomorrow, is to rewrite your original fraction, which was 1 over x plus 1 times x plus 2, as a sum of two fractions, each of which has one factor as its denominator. So a over x plus 1 plus b over x plus 2. So then you have to figure out the a and the b. And those are what you call partial fractions. Your high-end graphing calculators will do partial fractions for you. And of course Maple will, or Mathematica, or MATLAB. But I'll show you an efficient way to get them if you were doing by hand. So anyway, that's what the next section is about and what the class is about. So I'll see you tomorrow.